Now that we've solved and have some water levels exported from HEC-RAS, we're ready to bring them back into 12D for presentation. In order to do this, we'll move up to our design menu, back down to our rivers, HEC-RAS interface, and read HEC-RAS reports. Now it's already loaded with the values from our export. What happens is the import and export packages, our panels, talk to each other. When you select process, it records these settings. If you had hit the X value button up here in the corner when you left the exporter, these wouldn't be loaded and you'd have to select them. Now we have to select our river strings model. The source strings are not required for the results because the easting and northing data is contained inside this RAS export file. The ground surface tin that we're going to be working with once again is our survey and buildings, and we're going to be reading this back in from the GIS format from HEC-RAS. These are the results data. These are the new models that will be created: water levels, water surface, and the boundary strings. We'll talk about these once we create it and run it for once, and we'll also talk about what this chord length is for. Alright, let's process that, and you'll see that it happens fairly quick. It's finished, and we'll now take a look at the results that were created. To view the results that we've read back in from HEC-RAS, let's finish our panel, maximize our plan view, and turn off all the models on that plan view. Then we're going to come up and add on the water levels. Now what the water levels are is they are the 2D levels that have come back from HEC-RAS. If I was to toggle on my Z values and zoom in a little closer, you'd see that's exactly the same Z value all the way across these sections. The other thing you might notice is if I toggle on my vertices, that these are created at 10-meter intervals as across the strings. That was the chord length that we specified. Also, of course, if our source string bent, there would be an extra vertice where the bend occurred. Let's toggle back off those Z values. The other model that was created on the import was our tin. And if we add on our tin water surface, so once again I hit the lowercase tin on my T on my keyboard, you'll see that we've got our water surface profile. Now if it's a good set of results, we would expect for these contours to be perpendicular to the directional flow. Now if we'd like to take a look at this tin, we can also toggle on our tin solid and see that it goes the full extent of what we call our boundary strings. Now, if we come back on now and let's add on our add on the boundary strings. What these are is these are the intersection between the sloping water surface and our ground surface. So you'll see here how essentially the river follows along in this area here, and this is the part where we have to be careful of, is that we have the water flowing down in this direction, our river bends back in this direction and then flows. So we're going to do some extra work in this area in order to make sure that our flow stays perpendicular to the contours of our water surface tin. Let's now take a look at why our water surface contours are not staying perpendicular to the river as we move through this area. I'm going to toggle back off our tin solid, and I'm also going to toggle off those vertices. And if we take a look at our sections, we have one cross section in this area, the next cross section is way over here, and nothing in between. Now HEC-RAS is not concerned with the fact that the river does a bend like this, but when it comes time to do the mapping, it is significant. So what we're planning on doing here is reshaping this shape of our tin so that it will now follow our perpendicular to our direction of flow. And this is what we're going to use shape strings for. Now shape strings are going into a new model. I'll call them shape strings. And this one is going to have more than one point, so I'm going to go to the multiple points. And the idea here is that everything's looking good inside this area, but it's inside this reach when the water should be starting to turn and flow perpendicular to the river. So if I'm looking through this reach here, I would expect that a cross-sectional perpendicular line would come about this pattern. So I'm going to start mine about there, bring it into where I expect it to be perpendicular to the flow, so across there. And then in this area, I'm happy with the way that's going perpendicular out there, so bringing that all the way across. Now what that is going to do is it's now going to have my tin sloping in this direction. But I'm going to have to do that several times again, once for inside here, once for inside here, and then finally again perpendicular. Now that's going to make them quite close up at this end. So once again, I'm going to start back here. I'm going to bring that in. My plan is to come into about this spot here. Make sure I'm going perpendicular to the direction of flow across the river. And then once again, it will wind up bending back out if I was to get any higher flows. And I'm going to repeat this twice more. I'm going to bring that into here. Now I don't want my shape strings and my source strings to intersect each other. First of all, they shouldn't if the water is going to stay perpendicular to the direction of flow. And also, when we triangulate them to form a tin, we don't expect to ever have crossing break lines when we're creating a tin. Now, in this area out here, I'm not going to be too careful what I'm doing because I'm not expecting the water levels at this time to get to those areas. If I was working with much higher water levels, I'd be very careful about what I've just selected inside this region here. So I'm going to create one more shape string here. We'll bring it from the edge. Oops, but come back again. And once again, looking at the flow coming perpendicular through this area here, I'd probably bring that back to about here or so. Bring that perpendicular across the direction of the flow. And then, of course, we can't have these things crossing, so we'll bring that back out and bring that down to the edge of the project. So hopefully now you can see what the shape strings are for. They will not recalculate any of the energy losses. HEC-RAS says that it's going to be a flat surface as it follows the river. We're not going to do that. Change that. We're going to keep it as a linear changing water level as we follow the center line of the river. Now, for the rest of the project, it looked fairly good. In an area like this would probably also be a good case for a couple of shape strings. So let's just put a couple more into this area. So once again, the idea would be to start here, come perpendicular to the direction of flow, bringing that across to about the same limits. Oops. Once again, do that for the center here. Now trying to go perpendicular to the direction of flow. And we could add one more. Now this one should be coming across at an angle about like that. So starting up here, bring that down roughly to the edge of the river. It should be flowing perpendicular to that. And then bringing that back out where we expect the velocity to be in this direction in the overbanks. Now that we've drawn the shape strings, we have to re-import to have 12D recreate the water surface tin and the boundary strings. So once again, back to the design, come down to our rivers, back to our HEC-RAS interface, read the same results, only this time we're going to use those shape files, shape model. So we selected our shape strings now. We're going to reprocess that. And now if we zoom in a little bit closer, what you're going to see is that now the water surface contours are perpendicular to the direction of flow as the water moves to the rivers. So shape strings can be a very important part of doing plan presentations to accurately represent the sloping water surface along the river. Now that we're confident that our water surface is perpendicular to our river, we can be more confident that our boundary strings are correct. Now these boundary strings are often the only results that people are looking for after importing the data into 12D. So let's take a closer look at how they're generated. Going to the minus button, we're going to turn off everything except our boundary strings. Now when you review these boundary strings, you'll notice that there's an extra section out here. What's happened here is that inside this area, the ground surface is below the water level over here inside the river. So if there was a connection, it would be flooded. Now it's up to the user to decide whether or not to delete this boundary string or to keep it, indicating that flooding is possible inside this area. If we wanted to check to see how this was created, we could go up to tins, down to inquire, and look at depth between tins. The two tins would be, of course, our surveyed buildings, and the new tin would be our water surface. Inside the river, we're looking at a positive depth. Outside here, we're looking at a negative. Back inside here, it's positive again. The other feature that we have downstream is an island that's formed. Now we'll come back and talk about the significance of this island, but generally if there's small islands that do not significantly impact the head losses or the flow balances around either side, then this is a good representation. To see how these are actually created, not actually created, but what they look like, let's go over to our 3D perspective view. And we'll come into that 3D perspective view and add on those boundary strings. Now in order to see the boundary strings, you'll see that they're very lightly colored in this area. I'm going to turn on the orbit, swing our view around just a little bit here, and then just zoom in just a little bit into this section. Now if I was also to come and add on our tin water surface, you would see that these boundary strings are where the water surface directly interfaces with our ground surface tin. So the calculations are quite complex, but we do have a sloping water surface that we've made sure is perpendicular to the directional flow, and that has been intersected with a ground surface tin in order to accurately give us the flood inundation limits between the calculated sections. Now if you're looking at this in 3D perspective and you do have your tin, you'll also notice that if we back out a little bit, that those areas out here are also colored because it's assumed that it's flooded. If you wanted to remove these, which we will do, you would have to null the tin back to these boundary strings. The other thing that's often done in the 3D perspective view is to make the water surface transparent so you can see through it. In order to do that, you'd go up to your view, come down to visualization, and come down to your tin render settings. We would go pick up our water surface tin, and what we'd like to do is to make it semi-transparent by making the blending down to a factor of about 0.5. Hitting the set button on that, selecting finish, you'll now see that the water surface has become somewhat translucent, and we can see on the edges the boundary strings, and we can see the ground or the bottom of the river between the flood inundation limits. If you decided that you did not want to show this area out here as being flooded, you would have to null your water surface tin back to these boundary strings. So let's take a look at how we would do that. We'll move across back to our plan view, and what we're going to do is we're going to use this boundary string here in order to null back the water surface. So let's come and add on our tin water surface just so that you can see what's happening with this, and toggle on the tin solid to make it a little bit easier to see. Now we'd like to send that into the background, so our view menu button, models, models to back, tin water surface. So what our job here is to null this back. So we're going up to tins, down to null, and we're going to null by polygons. Now the tin we're going to null is our water surface, and we're planning on null, and we're going to null on the outside of it, and we'll use this option to null on accepting the polygon. Makes it happen a little bit faster. And the polygon that we're going to choose is of course this one here. Accept that, and you'll notice that it tells us that there's been a bad polygon and that the polygon has got duplicate points. Now let's take a look at what we can do to this polygon to stop it from being a bad polygon. The most common reason that a polygon is considered a bad polygon is overlapping vertices. So let's take a look at removing those vertices. We'll go up to Utilities, and we're going to use a filter under A to G, Filter, and the filter we're going to use is a vertex filter. So we're going to do it for the entire model, and the model that we're going to filter is going to be our boundary strings. Now the dimension can be either 2D or 3D, but we're looking at just the 2D, so we're going to need an XY tolerance. Now we'll keep this fairly small, so we're going to make it a 10 millimeter tolerance. And then it has to happen is what happens if there's attributes along our boundary strings. Well, our boundary strings don't have attributes, so we don't have to worry about them. But if you were ever doing it for another one, you might choose either to merge the attributes or lose them. Usually merge is the one that people will use for that. And we don't need a copy of these, so it's more than happy just to replace that and select filter. And it tells you that 6 duplicate points have been removed from that boundary string, hopefully making it no longer a bad polygon. However, there might be still one thing left to do. So let's go back and give that a go. We'll go and run that one more time. We're going to hit the pick button, come across, select that polygon and accept it. And it tells us that there's still a bad polygon. And we'll take a look at that one extra feature that we'll have to do to make it into a good polygon. Another common reason for a polygon to be considered a bad polygon is an overlapping first and last data point. Now we're going to turn off our tin water surface just so that we can get a closer look at this one. And now I'm going to toggle on our vertice numbers to help us see where the beginning and the end of the string is. Now you can see at this end we're up at the 200, so it's definitely not in that area. We're down to the 132 or so down here. So definitely it's going to be down in this area. And here we go, we're down to about 5, 7, 6. So it's definitely down at this end. And you can see if this was 2 and this is 524, that point number 1 is duplicated inside this area. So what I'm going to do is select the delete, come back, and remove one vertex. I'll get rid of 524 there to remove that one segment. Now 12D just assumes that there is a line across there when it uses this polygon. So now if we come back and just pick that polygon one more time, you'll see that we no longer say that it's a bad polygon, it's been accepted, and that the triangles have been nulled. So now if we were to come back and to add on our tin water surface, you can see how it's been nulled back to the edge of those boundary strings. Now another advantage of nulling that back is that if we went to our section view, where we were looking at one of our cross sections, and I came on and added our tin water surface, the tin water surface is now trimmed back to the edge of our cross-section strings. If we had not done this nulling procedure, that water level would have been shown all the way out to the edge of our cross-section and not looked very good when we went to do cross-section plots. Our last nulling procedure is going to be how to null the islands that are on the inside of our boundary strings. If there is only 1 or 2 islands, we'd leave it as the null mode, but we'd change it to null on the inside. Then we'd select the polygon, island by island, and you'd see we'd quickly null those, so we'd no longer have the water surface active where the islands are. Now if we had 10, 20, or hundreds of islands, this would be a very slow process. In order to speed that up, what we're going to do is we're going to fence our boundary strings so that all of the islands wind up in a model for themselves. To do this, we're going to use our utilities, fence routine. First of all, the data that we're going to fence is our boundary strings, so we'll pull that out. And the polygon we're going to use our fence. Now we have a bit of an issue here that if our data and our fence are in the same model, it causes a certain amount of grief because our fence will get somewhat in, somewhat out. So it's much better if we take our fence and put it into a model by itself. So I'm going to go up to a strings edit change, and for our boundary string, I'm going to put that into a new model. So I'm going to put that into boundary strings, and I'm going to add it fence. So it's the main boundary string that we're going to use. I'm going to go pick that. It's going to be our outside one. So now it's been moved into a model by itself. And I can come up here and I can add on that boundary string fence, and now it's in a separate model. So easily done. Now I can go and I can pick this. I'm going to go pick that boundary string fence, and I have to pick the model that all the islands are going into. Now I'll put that in as islands, and I'm sure it's clear by now that if we only had one island, this would be way too much work. But you can imagine if there's hundreds inside here, then this would be worth it. Alright, now as soon as we select fence, what's going to happen is now we're going to have a new model called islands, which is just going to be the data on the inside. So let's go and turn off all of these models right now and take a look at the new one that we've created called islands. And you can see it only has the one island. Now, the beauty here is that now we can use a model of islands to do the nulling. And so what we would do is we'd say go pick those islands and hit the set button, and once again it would null inside. Now we had already nulled that one, so if I turn back on my tin water surface, of course it's going to be nulled, but that would have done hundreds of them at once if that was our state.